谢谢君宝的介绍，非常感谢这个有这次机会来基础科学会议来讲这个一个工作。我相信有一些听众都已经听过我这个工作，但是我今天可能讲的更加 pedagogical 一点。我原来以为这是30分钟的报告，还有1个小时，我很高兴。这部分工作主要是基于我和我的2个学生曹旭还有董静，以及妮玛和他的学生Carolina， 我们在去年年底完成的3篇工作，还有1篇希望这个月能够出来的工作，以及我会提到一些相关的工作。这里非常重要的一个基础是妮玛和两个物理学家和2个数学家完成的一个奠基性的工作，就是把这个组合学的这部分搞清楚。那么我们这个工作等于是基于这个组合学的工作去把它应用到所谓现实世界的散射指的是什么呢？就是实际上目前我们只能够做在任意圈在圈图水平上，就我们相信到任意圈水平上，我们能够做派介子和胶子的散射，也就是所谓的 nonlinear scalar model 和 Young-Mills 这2个理论。当然，在树图你可以把这个组合学的方法应用到更一般的理论，我后面会提到。那么我这个讲的大的背景就是说有 amplitudes 这样一个多个领域的一个交叉的一个可以说是一个窗口吧，让我们可以从我们以前很难想象的一些现在能够做的这种微扰的计算也好，甚至有一些是基于像特殊理论中的可及性的或者严格求解的一些结果，能够去窥视很多不同领域之间的一些联系。比如它的起源是来自于这个对撞机物理，就是说这个精确量子场论中的高精度计算，以及它可能在这个对撞机方面的一些 phenomenology 方面的一些应用。那么这个仍然是目前推动这个领域向前发展的重要动力，因为大家需要把这个比如说标准模型的标准模型中的一些散射振幅计算的非常精确的，比如 QCD 之中的这个包括怎么得到这些圈图的贝积函数和把这些费曼积分积出来，对吧？那么在这个的研究的过程中，大家就发现，其实关于量子场论本身，我们有很多没有理解的事情。比如说散射振幅，我们通常指的是它是在鞘的这样一个物理量，但是现在也有很多工作把它推广到离鞘的，比如说你有这个形状因子，那么有一点点离鞘，对吧？到了关联函数呢，就是完全离鞘的这个这样一些物理量，这些物理量内部都有一些，像散射振幅是最早发现的，其他的物理量可能晚一点发现，都有一些深刻的结构。这个结构我指的是，比如说它比它的计算过程中的费曼图要简单很多，然后它甚至就是任意圈你都可以把它的结果给写出来，或者说它有一些新的数学的结构，大家以前没有意识到。所以说它和数学的方面，我今天会讲到这个和几何还有组合学，包括这个怎么做费曼积分这边和很多这个特殊函数数论方面的事情的联系。总的来讲，就是我们意识到，不管是对于规范场论，还是对于引力，甚至对于一些我们以前没有意识到，比如说有效场论，一些关于 Goldstone particle 这种 Goldstone 粒子的有效场论，都有新的物理和数学在这里面。然后呢，它另一些联系呢，可能主要是和这个弦论和量子引力，包括经典引力方面。那么近些年大家也有很多发展。我们知道弦论一直也是这个领域的推动之一，可以说。大家经常说这个最强大、最完美的 S matrix program 就是弦论，因为最早大家知道弦论的微扰弦论，我只能说弦论的一部分就可以应用在可以被当作是一个最完美的一个 S matrix program。为什么呢？因为其实弦论的发现就是随着这个 Veneziano amplitude 的提出来，然后大家就是想在弦论中，我不用去在 bulk 里面去对费曼图全部都求和，而在一个世界面上的这样一个 CFT。它的关联函数可以给出散射振幅，这个实际上是跟我们现在这些 idea 是非常接近的。只不过可以说最近30-40年，大家把类似于弦论这样的，我用一个别的计算方法，不是 bulk 里的费曼图的这个相互作用，这个 bulk 里的这些一张一张费曼图加起来的方法，把它应用到粒子的散射，而不是弦的散射。比如说 Witten 的扭量弦论，或者 CHY 或者其他的一些我后面会提的。当然有这个经典引力方面的应用和。这个 ADS 中的散射振幅或者宇宙学中的散射振幅，这些都可以看作是平值时空散射振幅的一个在弯曲时空中的推广。OK， 那这是一个大概的介绍，大家有问题的话随时打断我。那么我今天想 focus 的主要是可能是在就是在这一块，就是说在这个formal 的量子场论、弦论和数学之间的发现的一些新的结构。那么这个结构我说了，最早其实就是来自弦论的这个膜空间。我们在这个 genus G 的黎曼面上，如果 n 个 puncture 的这样一个 modular space， 对它的研究实际上是非常重要的。就是这个可以被看作是整个我们说散射振幅 或者说包括刚才提到的弯曲时空的推广啊、关联函数这些推广，它背后我们说有一种叫做组合学的几何的这样的一个概念。它的第一个例子就是 modular 空间，因为 modular 空间它实际上它定义本身，你说有一个黎曼面，然后上面放一些 puncture， 它的模空间定义本身跟我们说时空中的这个散射粒子的散射好像没有什么关系，对吧？但是它其实有类似的这个组合学的结构。我们说，比如说树突振幅最简单的一个结构是那些粒子散射的时候，你跑到一堆粒子动量加起来 on shell 的那个地方，它才有它的singularity， 有一个 pole， 在那个 pole 上面，它的流数会因子化 factorize 成2个低点振幅的乘积。那么这个性质模空间也是有，就你跑到genus 0的黎曼面上，你说它的边界是什么？就是一堆点拼接到一起，它变成了2个低点的这个黎曼球面的乘积了，这样的一个故事。那么当然它有它的圈图推广，圈图的时候你就不只是在这个做 pole 上面的 factorization， 你可能要跑到这个 cut 上面，对吧？因为圈图的函数更加复杂。那么这个黎曼面的这个高规格的黎曼面的一些性质也会和我们说的圈图振幅的这个最基本的在组合学的意义上是等价的。如果是就是我的理解啊，如果是标准的微扰弦，以前有的问题也还是没有解决掉，可能就是有一些通过别的方法，像 pure spinner 什么，大家试图在做这些问题，但是我不认为解决掉了。那我现在讲的呢，就是我只用这个曲面，我只用这个 genus G 的曲面，有 n 个 puncture 这个曲面，研究它的一些组合学性质，然后把它用在甚至只是用在粒子的散射上，这个。不用弦，对，不用弦，只是借它的曲面来研究粒子的散射。这一点上，似乎任意 genus 都没有本质的区别，就是没有原则上的困难。计算上可能会随着 genus 的增加会越来越麻烦，但是 idea 是一样。所以我后面会讲，就是其实还是在利用第一个这个最原始的这个 idea。那么中间当然经历了很多别的发展，我也不进入细节了。就是尼玛他们从大概10来年前开始发展出一套叫做 positive Grassmannian 这个东西，这个东西跟弦的这个空间是非常不一样，但是它可以用来描述这个另一个我们非常喜欢的理论，就是这个4维中最大超对称的这个杨缪斯理论，它被称为这个，对吧？就是21世纪的或者量子场论中的谐振子或者是氢原子，取决于你或者是 Ising model。那么它的这个任意圈的散射振幅似乎都可以被 encode 在这样的一个数学上的一个也是有着这种组合学概念的一个 factorization， 由它就引出了像 amplitude， 包括回到3维这个 ABGM 理论的 amplitude 这样一些 idea， 这些 idea 和原来的弦论的这个模空间是正交的，它看起来没有什么关系，它是必须限制在4维和3维。cut， 对。那我们现在用的呢就特别简单，我们现在就研究圈图的那个贝基函数。那么所有东西都是极点了，只不过这个极点有的是涉及圈动量的，有的是不涉及圈动量，所以就等于所以我说我们比弦论要简单，而且比场论振幅也要简单，因为我们是场论振幅的贝基函数。这个曲面上的任何结构都搞清楚了，相当于那么所以说，在最近5年左右，大家又回到了这个 theme， 回到这个 theme 的一个关键是大家提出了一个，就是从 CHY 开始，大家开始研究一个特别简单的理论，就是等于又退回到最简单的理论，叫 phi3的理论。当然，这个 phi3是带有color 的，所以说它不是一个把所有图都加在一起，而只是把比如说在树图的话，把平面图加在一起的这个 phi3理论。它的研究导致了我们发现，哎，原来在这么简单的任意维度的一个 scalar 理论里面，我们也有一个几何体，这个几何体它也有组合学的边界，这样一个 association 这样一个几何体。那么我后面会介绍它。那么它和弦论的 M0n 这个开弦的 M0n 的这个模空间是直接联系的，因为它们2个有一模一样的组合学边界，就是都是一个叫做 association 的边界。那么所以说，最近几年的这个发展就是希望从这儿跑到任意圈，然后我们最新的发展是把它从任意圈 phi3 推广到任意圈的，比如 non-linear model 和杨缪斯。OK， 那这是一些其他的发展，比如说我们可以同样的做这个 cosmology 的问题，或者是费曼积分中的一些也用到这个一样的 idea， 对吧？这里这个就是过去3年尼玛他们在做的这个事情，就是说树图的 M0n 是一个 association， 那么圈图的这些 M1n、M2n 这些开弦的或者说就是曲面吧，就是说这个 genus 更高的这个 有边界的 n 个 puncture 的这个曲面，当然也包括非平面的推广，就你可以在里面的圈里面也放 puncture。这些曲面它对应的几何体是什么？这个是个很重要的数学问题，他们最近几年解决了这个问题。好，那么这个是一些其他的工作，我其实今天不会细讲，但是我想说，就是对这个对刚才的这个 list， 我们可以有一些新的发现。实际上，在过去半年左右的时间里面，已经有很多新的发现。比如说，这个是我们发现说，关联函数自己也有一个非常像这个 amplitude 的一个几何体。amplitude 是一个在翘的振幅的结果，它的任意圈的被积函数可以表达出来。那么至少对于4点关联函数，它可以看作是在翘振幅的一个离翘推广。就你这些点之间不再是 light-like 隔开的，而是任意的。它的 x1减 x2的平方不再是0了，对吧？任何2个 x 的平方都不是0。那你就简单的把 amplitude 的几何定义推广一下，你发现，哎，这个推广是 work 的，就是你可以现在看到它到3圈甚至4圈，我们目前做到4圈为止，它的这个可以说 ADS-CFT 里面研究的历史最悠久的物理量之一，叫做这个2222这样一个关联函数，它的被积函数一直到4圈都是有这个几何的解释，也就是说我们都可以用一个 amplitude 的这个离翘推广来描述它。OK， 那么这个也包括有一些 cosmology 方面的进展，这个我们的文章应该马上就出来了。就是说刚才说的是平直时空的，那么你也可以把这个类似的 idea， 就是这个相指是 polytope 这个 idea 去推广到这个宇宙学中的严格来讲是宇宙学中的这个波函数。这个波函数可以看作是这个散射振幅在 de Sitter 空间或者在 FRW 背景下的一个推广。那么还有一个就是 ADS 中的一个推广，这个是很有意思的一件事情。我觉得就是这是非常有就是说未来我觉得会有更多进展的一个小方向，就是说无论是研究在 ADS5 乘以 S5 中的这个超引力振幅，还是 ADS5 乘 S3 中的这个所谓的super young muse 里面有这些胶子和 scalar 这个 anyway 这样的一个 couple 的一个理论。它这个里面所谓 ADS 的散射振幅，指的是它的 boundary 上那个 CFT 的它的关联函数，对吧？它的 holographic correlate。那么对它的研究，本来是这个看起来跟我们现在讲的这个散射振幅这个主题非常没有关系，它是一个 CFT 中的 correlator。但是你把它变到 Matlin 空间中，你发现它有2件事情非常非常像散射振幅，一个是它也有这些 pole 结构，甚至我就是用这个 association 一模一样的变量在描述它这个 pole， 唯一的区别是在 amplitude 里面这些 association 的边界的这个 pole xij 要等于0，而在 ADS 里它可以等于什么-2、-4什么样的就是 descendant 的 pole， 这是它唯一的区别。那么第2个性质就是说，我们会发现，哎，它也满足跟 amplitude 一样的 recursion， 就我们叫 constructibility， 就是我给了你最低点的，比如3点的这个振幅，你能否用刚才说的在这些 pole 上的因子化行为去把高点构造出来？就你知道因子化行为是一回事，但你能不能就是说所有的 pole 都知道了，就是你能不能就是说把所有的，因为这里主要的麻烦在于，如果它的交换的是个 scalar， 这个 factorization 很清楚；如果它交换的是个spinning 的 particle， 一个 gluon， 这个 factorization 就非常麻烦，就是这跟平直时空就麻烦很多。那么我们可以通过这样一个 recursive 的一个过程，说每次只允许一个 gluon 在中间传播，证明了这个东西到 n 点确实是 constructible。那么这个在比如说去年的时候，大家都还只知道这个理论能算5点或者最多是6点，就是4点。我刚才提的所有事情4点，大家已经算得非常非常丰富了，不只是外腿都是2的情况，外腿有更高的 charge， 包括1圈、2圈都有结果，对吧？但是5点、6点开始几乎没有结果。那么我们用这个方法，就是不仅证明了它到任意点都可以通过因子化，就跟有点像 BCFW recursion， 不过是一个 ADS 的版本，你可以把它 recursive 构造出来，而且你确实可以算出这些结果跟平直时空的结果很像，就是说它会有跟我下面会提这个 association 推广到 young muse 那边很像的一个形式。所以说这个方向，我认为接下来会可能会有很多的发展。如果对这个既对这个平直时空的这个几何和组合学感兴趣，也对这个 correlator 感兴趣的这个一个交叉吧，我觉得这是很有意思的啊。这是数图，我现在讲的数，就是目前为止所有的1圈图和部分2圈图的结果都是关于4点，就是没有任何5点开始，大家还不知道在圈图怎么开始做这个事情，就是这个 CFT 的 data 还太少。但是数图你可以通过这个 recursive 的方法一直往上走。好，那现在进入正题，就是我主要想讲的是这样一个故事，说我们怎么从一个 toy model， 这个 toy model 就是 Chase phi3，这个是被称为是最简单的这个 color 的理论，就这样一个理论。它是一个，这是它的 kinetic term， d phi 平方，对吧？这是它的 phi3，你能写出的最简单的理论。只不过这个 phi 是一个 n 乘 n 矩阵，对吧？这是 sun 下面的一个或者 un 下面的一个表示下面的一个矩阵。那么你做它的费曼图展开的时候，它实际上出来的是这个，你用这个 double line notation 的话，是我们叫做这种 fact graph， 就是 Tuhuf 当时引入的这样一个东西。那么这是个非常简单的理论，因为它为什么呢？因为它没有分子，它都是1除以这个 pole， 就是它都是传播子乘起来这样的一个东西，包括它的圈图的贝基函数，只不过它传播子现在开始涉及圈动量。所以说我们把这个最简单的 color 理论，但注意这样就算是这样一个最简单的 color 理论，如果你想把组合学彻底的搞清楚，因为它的组合学的树图就是我说的 association， 就17年我们搞清楚，但是到19年的时候我们搞清楚了它一圈，然后一直花了尼玛和那些数学家3年时间，到大概22年的时候，他们彻底搞清楚了这样一个最简单的理论，但是它到任意圈就在任意规格的这个曲面上，它的组合学性质是什么东西？他们写出了一个公式，这个公式可以到任意圈描述这个理论，所以说它还是有非常丰富的这个组合的这个结构的。但是无论如何，它是一个这样的理论，它只有 denominator， 它没有分子，对吧？那么我们会想说，哎，怎么去从这样一个理论去理解一些 non-trivial 的理论？这个我可以做一个类比，比如 Super-Young-Mills 这个理论 ，n 等于4 Super-Young-Mills 也是著名的一个，它有所谓的 dual conformal symmetry。所以你简单来讲，就是说它的所有的行为都是由它的，因为有这样的共形对称性，它的所有的行为都可以被它的红外的这个，就是这些 pole long distance 的物理来描述。Sorry, maybe I should switch to English. Hey, good to see you. So the goal here is really to move to more realistic theories based on what our understanding of trace by cube, the simplest color theory. So very natural questions you can ask is what are the zeros of this amplitude? So it turns out that the trace by cube has very rich pattern of zero, where you set some Mandelstam to 0, the whole amplitude vanishes. So this is not manifest in Feynman diagram, but we'll see that it becomes manifest in the association and in the stringy version. So more interestingly is really about the stringy version. So the stringy version tells you that the nonlinear Sega model and the Young-Mills can be viewed as the same amplitude of the stringy phi cube, except that now you need to shift the kinematics at some different positions. So that's the only, so the same Veneziano Koba-Nielsen amplitude describe you not only the string version of trace phi cube, but actually also in the field theory limit, also the pions and the gluons. But the gluons we have to explain, because the gluons depend on polarization, but now we're really in what I just mentioned, the scaffolded fashion that each gluon corresponds to a pair of scalars. So this story about finding zeros, and there are some factorizations near the zeros, and then which give you the same description for phi cube, nonlinear Sega model, and Young-Mills in a string formula is at tree level. But now from there you can naturally, because trace phi cube, the stringy trace phi cube story has been generalized to all loops based on the surfaces. So that's why you can for nonlinear Sega model, you can easily obtain the all loop integrand for nonlinear Sega, and for Young-Mills, we still have we have a conjecture that it also works for loop integrand. Okay, so let me get into a little bit detail about this theory. As I already mentioned, this is in the double line notation give you this fat graph expansion, and it's really the simplest theory in the sense that you are summing over all triangulation of a given surface. And then for each triangulation, you're taking the product of propagators, nothing else. There's no numerator. So this is the 4-point amplitude and 5-point amplitude, where xij is just one particular curve or chord, or in the tree level case, it's just a diagonal of the angle. And there's something interesting you notice, that the usual Mandelstam, pi.pj, where the I and j are non-adjacent, is given by this combination. So you can translate between these planar variables and the non-adjacent Mandelstam in this way. Okay, so there's a dual formulation of this dumb theory that just summing over triangulation and product propagators is given by the so-called volume form of a sociohedron, where you build your polytope by restricting to a n-3 dimensional subspace, exactly by asking a bunch of C, this non-planar Mandelstam variable to be constant, but not all of them. So for example, the usual realization is you ask all the Cij when j is not n, j is at the most n minus 1 to be a constant. Then you ask all the planar pole to be positive. This carve out a polytope for you. Okay, so if you compute this canonical function of the polytope where you have only poles, logarithmic poles at boundaries, you get the phi cube amplitude. This is a very simple story. But this, so this is a particular, this is a way to visualize this. So you put all the planar variables in this grid, okay? So this is I-axis and this is J-axis for the Xij. So in each diamond, in each small grid, you have the Ij, I plus 1, Ij, I plus 1, J plus 1, I plus 1, J, and the Ij plus 1. You have the sum of this top, bottom, minus the left and minus the right guy equals the C. So you put the C here, okay? So this is the infinite grid. But what I just told you about the realization of a sociohedron is you have to find a region which contains all the Xij variable once and only once. So that will be a allowed region, or this or that. So once you choose this region, of course, you only include some of the C's. For example, if you choose this region for the 6 particle case, you exclude all the Ci6, right? Cin. So that's how you only have the right number of C to give you an n-3 dimensional polytope. And you have other choices. So any choice of the region give you a realization of the sociohedron corresponding to some initial triangulation. Say this is the hexagon case. And you also notice that if you view this as a discrete version of like a 1 plus 1 dimensional wave equation, then this is the Gauss law, right? You just when you're summing over the whole big causal diamond, this combination is given by the sum of the C inside this diamond. Okay. So with this realization, there's a little surprise coming out from this polytope picture, which is if you set a bunch of Cij to 0, the whole amplitude vanishes. So this is a bit hard to see in Feynman diagram, right? So if you put 5 denominator together, this is like a cubic polynomial in the numerator. How do you know which Mandelstam to set to 0 to make it vanish, right? But if you look at the polytope, it turns out to be very simple. So if you look at the match picture, let me give you the answer first. So any small diamond, any diamond that span from left to right, if you set all the Cij in this diamond to be 0, the amplitude will vanish. So in the case of this skinny rectangle, this is what we call a skinny 0, which is very close to soft limit. You set P1.P3, P1.P4, all the way to P1.Pn-1 to 0, the amplitude will vanish. I mean, this is not a soft limit because you are not setting P1.P2 or P1.Pn to 0 because those are adjacent guys that appear in the denominator. But anything else you set to 0, the amplitude will vanish. And you can also generalize to, for example, this 2x2 grid. When you set it to 0, the amplitude will also, trace by cube tree amplitude will also vanish. So you can see this directly from the sociohedron picture because whenever you set some C to 0, the sociohedron actually starts to degenerate. So when you set enough C to 0, the sociohedron collapses into some lower dimensional thing whose canonical form is just 0. Okay, so this is how you see 0 geometrically. And this also tells you something about the behavior near 0. Because in the last step, when you set all the C to 0, you get 0. But if you turn on one of them, so you see that if you turn on one of them, the sociohedron looks like something like with some top and bottom piece times the height, right? So this is a factorization, basically. I mean, in the 5-point case, it's too trivial. When you turn on one of the C, it becomes a 4-point guy that's proportional to that C. So these two guys add up to C13. So if you further, C14. So if you further set it to 0, it will vanish. But times some left part and right part. But here it's just too simple that the left part is 3 points. So there's only a 4-point guy. If you look at a 6-point example, when you set 2 of the C to 0, it's a 4-point times a 5-point times 3-point. Or it's 4-point, the middle guy 4-point times left and right, which are both 4-point, depending on which C you. So this is the 2x2 guy if you turn on one of them. Okay? So this is a general picture. For just in this realization, for any rectangle, if you set all of them to 0, you have a 0 of your amplitude. But if you turn on one of them, it becomes this up amplitude and this down amplitude with some shifted kinematics. So they're actually times this 4-point guy in the middle. Okay. So let's see this again from for finite alpha prime, because I told you that the whole thing that allow you to generalize to all loops is actually based on the stringy trace phi cube. So the stringy trace phi cube is this Veneziano Corbanius amplitude that's known from the 60s that we just these are written in terms of the worldsheet variables, but we just reparameterize it in terms of this positive coordinate. Okay. So once you reparameterize in positive coordinate, it has something to do with the immediately related to the pseudohedron picture. So on each rectangle C, you put a polynomial of this positive coordinate. So the string integrand will become this polynomial raised to minus Cij in the exponent. Okay, so whatever Cij you turn off this polynomial, the corresponding polynomial in the grid. Okay, so for example, in the 4-point case, we know very well this is a one-dimensional integral dy over y with y to the x and 1 plus y, that's your polynomial, to the minus C13. So this is the beta function. And for 5-particle trace phi cube string integral is a 2-dimensional integral with 3 polynomial raised to C13, C24, C14. Okay? So now you start to turn them off. What happens is that actually you don't have to set them to 0. You can set them to any non-positive integer, then the integral just vanishes. I mean, the integral vanishes by analytic continuation. I mean, this is the analog of the scaleless integral that in dy over y to some power, right? So given me any rectangle, I set all the c's here to be negative, a non-positive integer, it will always make the whole string integral vanish. And now I can turn on one of them. So if I turn on one of them, let's still stick to the case that they are all 0, and I turn on one of them to be arbitrary. You see that it's no longer vanishing because this doesn't happen, but you can single out a 1-dimensional integral which gives you the beta function times some left and right guy. Okay, I'm not going into any details, but this is the conclusion that for the old string trace phi cube stringy integral, if you turn on one of them, it's a beta function times this upper and lower. So that's a finite alpha prime generalization of the polytope I just told you. Okay. Here comes the connection to the more realistic theory. We've talked about phi cube, even at tree level. I mean, this is a Toy model, but at tree level, you can ask the question. Yes. No, this is all in general dimension. The kinematics, the space-time dependence is all in general dimension. Of course, the string. I mean, if you view this as worldsheet, that's the usual thing, but it's just this is some tachyon amplitude if you want, some tachyon amplitude of the yeah. Any other questions? Yes. Now I'm going to come to this point. So the claim is that the same integral that defined here with some shifted exponent, shifted kinematic point, will give you pion amplitude and will also give you some 2n scalar amplitude which contains n gluon. Yes, of course. Yeah. It's in general dimension, of course. Yeah. And here comes the shift. The shift is very easy. I told you about these u variables, which for each chord you have a u, and for even number of particles, the u variable come in. There are u even odd. The u even odd with exponent x even odd will be those poles that you can have for pions, for example. Let's focus on pion first. So you don't want to shift them. You want to keep them as massless poles. But now you shift other exponent x even and x odd. Those poles you don't want. You want to shift them away, so they become some massive. If you further send alpha prime to 0, actually you are sending this pole to infinity. This shift to infinity. So notice that this is a very unique shift because this is the only shift that keep all the C invariant, all the C unshifted. So all my conditions about 0 and factorizations are about the C's, right? So when I do this shift to my string integral, I mean, I just get some trace phi cube at a different position, but all my C's are preserved. So when I start to set those C to 0 or integer, the property that the whole string amplitude vanishes or factorizes still doesn't change, right? So right now I'm not telling you any physics, it's just the claim that when I shift these things in this particular way, all the 0 and factorization will remain. And it's just a coincidence that we also observe for pion amplitude and for so-called 2n scalar amplitude in this theory. You dimension reduce the Yang-Mills theory to contain scalars. So the scalar come with interaction with gluons and also the 5 to the 4 interaction. In this theory, if you consider the 2n scalar, the scalar come in pair, they all share the same 0 as phi cube. Okay, so that's a key idea allow us to connect all the theories, because if you imagine something to describe these theories and make manifest that they have the same 0 and the factorization as phi cube, that's the only possibility. No, those are zeros. When you set the Cij to 0, the whole amplitude vanishes. The same as phi cube, yeah. So it turns out the delta, if delta is a generic non-integer value, you get pion in the field theory limit. Okay, we can easily. I'll give you the proof in next slide. But if delta is a particular integer, then this is different. This changes the singularity structure of your trace phi cube integral. For example, it turns the dy over y into dy over y squared. So that will give you something new. And it turns out this gives you 2n scalar, which contain the n point, n gluon amplitude. Okay, so let's look at pions first. This is really simple because I'm shifting the string integral for any non-integer value. And when I send alpha prime to 0, equivalently, I'm just sending the shift delta to infinity. Okay, so this is not changing any. This is really a very trivial thing. So the claim becomes something at field theory limit. Just take the even point trace phi cube amplitude and do this shift. Now you send the shift parameter delta to infinity. You see that when you send it to infinity, of course you killed those poles, but it's still non-trivial that what you get at leading order is exactly pion amplitude. So for example, this is the 4-point example. You can easily see, and the 6-point example, you not only you're left with only the 4-point times 4-point exchange diagram, but you also have the correct contact diagram. Okay, so this is actually guaranteed because this shift will preserve the 0, and we know the theory that also have the amplitude that also have 0 is for the nonlinear model case. Okay, so you can easily prove that at tree level, since this has the correct pole structure and factorization, and also Adler 0, the Adler 0 becomes a consequence of the skinny 0 we mentioned, because when you take the skinny 0, now you can further take P1.P2, P1.Pn to 0 because the pion amplitude doesn't have those two particle pole, right? Okay, so the nonlinear second model 0 and factorization are now explained. I mean, 0 is very trivial, but let me say something about the factorization. For factorization, it's actually factorized into a 4-point amplitude times 2 odd point amplitude which are mixed. So you have pions coupled to phi in the factorization. Yes. It doesn't matter. Yeah. So it's just take any parameterization you want. You can. I mean, right now I'm computing just the tree amplitude of this model. Yeah. But now you can also go to loop level. You take the same idea that now you have a control of L loop, say planar L loop phi cube amplitude. You do the same shift, except now when you shift the Xij, this puncture could be a loop puncture. Okay, so you're also shifting loop momentum in this sense. But you don't know how to assign even or odd parity to your loop puncture. So the only reasonable thing to do is to sum it over them, and it turns out to be the right thing. The reason is also very simple. So when you sum it over even and odd for the loop puncture and do this shift, send the shift to infinity, you not only kill unwanted tree poles, factorization poles, you also killed unwanted loop so loop cut. Okay, some single cut that give you wrong tree are killed in this limit delta goes to infinity. So basically you can prove that not only factorization but all the single cut work for nonlinear second model under this shift. So that has to give you the correct nonlinear second model integrand. Okay, so actually this is a very nice integrand that you can even study some version of that Adler zero at integrand level. So you can show that when you send the momentum to be soft, the integrand becomes something scaleless. You can show this in general. So this tells you that this must be the correct all loop planar NRSM integrand. Okay. So here is something related to this story, but we developed later, which is it turns out this zero and factorization is some consequence of something more basic, which you can understand nicely at tree level at least. So this is something we call splits. Okay. So I have to say we still don't have a direct understanding what's the physical reason that amplitude was split into two currents when you send some Mandelstam to zero. So precisely if you pick 3 particles out and divide the rest of the particle into this set A and B and send all the SAB to 0, so any Mandelstam, any Lorentz product crossing these two sets to be 0, you see the amplitude factorized into 2 currents with an offshore lag on each side. So this splitting behavior implies the zero and factorization for phi cube nonlinear scale model and the 2n scalar Yang-Mills scalar theory. But this is something more general because now you can generalize it to uncolored theory. So everything I've told so far based on surveys are for theories with color ordering, right? So now you can do many other theories like special Galilean, DBI, or even gravity. Now you can do see that they all split. Of course, for theories with polarization, you also need to set the Lorentz product involving polarization to 0. So this is like really saying the n particle system decouple into 2 once you kill all the connections they have in this Lorentz product. But it's very hard to see in Feynman diagram or anything. So it's proven using the string formula or using the CHY formula. So you can I'm going to skip the details. So here is the condition for gluon or graviton, right? In addition to PA dot PB to 0, you also have some epsilon A dot epsilon B or epsilon dot P to 0. Then the whole open string n gluon open string amplitude splits into 2 currents. Okay. So these are the currents that for particles gluons in A, and these are the current with gluons in B with some off-shell lag. And same for graviton. So for graviton, you can make the various different ways of splitting the answer. And you can also derive, for example, like soft theorems from this splitting. Like if it's a skinny splitting, you just derive the usual soft theorem, soft gluon and soft graviton thing. But also for the Goldstone, I mean for those effective field theory like nonlinear scale model, DBI, and so on, you can see the Adler zero from this skinny splitting. So it's a very interesting question. Now you have other splittings, not only skinny, right? You have other bigger splitting. What do they imply? I mean, one way is that they tell you something about multi-soft limit. And Nima and Carolina also generalized this splitting for higher genus surfaces, which again only works for the color case, like trace phi cube or nonlinear scale model. But what they claim is that for any surfaces, you can have some way of splitting, and they are related to soft or multi-soft limits. Okay, so the last thing is I still haven't talked about is how to get gluons out of this shifted trace phi cube amplitude, the 2n scalar amplitude coming from the shift of trace phi cube. At tree level, it's very easy. I'll explain to you. But at loop level, this is still a conjecture. And so how do you use the surface integral for trace phi cube at loop level, do the same shift, and take alpha prime to 0 limit and produce you Yang-Mills loop integrand? That's still an open problem. We made progress at 1 loop, but higher loops still work in progress. So as I said before, this particular way of shifting delta equals 1. By the way, if you shift delta equals to other integer, like delta equals to 2 or something, you produce some higher spin theory. So you produce some pairs of scalars that each of them contain some higher spin colored amplitude, which we don't know what to do with them. But for delta equals 1,
this is exactly the 2n scalar in bosonic string. Because if you take the bosonic string and do this, go to this very special kinematics, all the epsilon dot p to be 0, and epsilon dot epsilon is only most epsilon dot epsilon are also 0 except for the pairs, right? So like epsilon 1 dot epsilon 2, 3.4, and so on, they are 1. If you go to this very special choice of the polarization of the 2n gluon bosonic string integral, you get exactly that shift I told you. Okay, so you start from some 2n gluon amplitude, you do this dimension reduction, you get some 2n scalar theory, but gluon propagating in the middle in the bosonic string case. And that is a one-term formula after you do this, which is given by the stringy trace phi cube this to the exponent 1, right? If this exponent is some arbitrary value, then it gives you pion. But if the exponent is 1, now I show you this is exactly 2n scalar in bosonic string. So how do you so you already see that this contains gluon amplitude. How do you extract it out, right? So you just take this 2n. So this is the formula that you have after you multiply this shift deformation parameter with exponent 1. It's exactly turning all the dy over y into dy over y squared. Okay, so you have some 2n form that's different from trace phi cube. It's a new form. It's no longer a d-log form. And now you want to extract some residue. You take all the residues where each pair of scalar become the sum of their momentum become on shell. So you extract the gluon out of it. And what are the polarization of the gluon? The polarization of the gluon is of course the p minus p, right? So at least in this choice, because this is the coupling of two scalar with one gluon. So that is the way I'm saying you shift your 2n point stringy trace phi cube amplitude to this dy over y squared form. And now you take n residues out of it. You get a gluon amplitude with this choice of polarization. Okay? So it's very, very interesting that to see, for example, the 3 gluon amplitude in Yang-Mills theory or in trace phi cube, in F cube coupling turn into this 2n scalar language. Remember, this x variable or this c variable describe you the scalar amplitude, but now it's for 6 scalars. Okay, so you trade the 3 gluons for the 6 scalars. Now you're describing the 3 gluon amplitude in terms of this hexagon language. And now at G level, everything works. So we have a very concrete recursion in general dimension now that give you n gluon amplitude in this 2n scalar language. You can really it's very similar to BCFW. Just use all their residues. But at loop level, this is much more complicated because so you can still write down at loop level this dy over y squared measure and take the residue. And the conjecture is that they will give you loop integrand where gluon, n gluon loop integrand where the gluon are described by pair of scalars, each gluon. But now you have a lot of complications because when you take this surface integral formula, you have all these intersecting curves. You have the so-called closed curve raised to some parameter you call delta. So what do they mean, right? So there are many things you can study here. For example, you can translate the requirement of gauging invariance and also factorization on poles into this 2n scalar language and check if your surface integral at loop level satisfy this. And there is a sense that they are satisfied. So we know that we don't really have a gauging invariant loop integrand. But this surface integral gives you something gauging invariant up to purely scaleless things like tadpole or massless bubble. And another thing you can check is leading singularity. So this is particularly simple. Now you are, if I give you a surface, it's defined by some triangulation. So it's naturally related to leading singularity where you glue 3 points together, right? Well, this formula is very hard to compute alpha prime to 0 limit with dy over y squared. It's very easy to extract just the leading singularity. So if you take every propagator on shell of a given triangulation, this turns into a residue computation of the surface integral. Okay, so we've checked up to 2 loops that the residue of this surface integral indeed agrees with the gluing of 3 points. The definition of this leading singularity for any cubic diagrams up to, and we also fix this delta. This delta has to be 1 minus d. The d is the dimension, to describe gluon propagating in D dimension. Okay, so this leading singularity check gives you a lot of evidence that this formula has a chance to work. So as I said, I mean it's already at one loop. It's very hard to perform such integrals take the alpha prime to 0 limit of such integrals. So right now we're using some other way that to really glue the tree-level gluon amplitude together in this scalar language to get a one-loop integrand. So this is the forward limit idea. I think Simon first studied, but back then the problem with pure Yang Mills is really the divergence, right? This 1/0 issue. But now on the surface, all these tadpole and the massless bubble variables are there, so you can put it there. So give it just give it a name. It's naturally given. This x11 variable is naturally the divergence you encounter when you glue two tree-level gluons in the forward limit. So in this way, you can show that actually the one-loop surface integral, you don't have to compute it. You just show that it has the correct single cut as gluing from the tree amplitude with two additional gluons. Okay, so in this way, we have a working recursion for one loop based on this single cut idea and the regularization provided by the surface variables. We have a recursion that works for one loop up to very high point, and even starting from one loop to do the recursion again to get two loop pure Yang Mills integrand. So there's this recursion that we checked up to one loop 6 point and two loop 4 point. They give you the correct Yang Mills integrand. So that's basically everything I want to talk about as a probably very early, still a lot of time. Let me just start. No, not really, because the surface is stick to. I mean, you can double copy, but that's a totally different story. So everything here is color, right? So it's at least I have no idea how to even at tree level. So at tree level, okay, this idea, this just variables. I mean, this idea of writing the n graviton tree amplitude in terms of each graviton is a pair of scalar. This idea still works, but it doesn't buy you anything because now you are dealing with the permutation invariant object. The surface variables xij and so on is not very practical anymore. Yeah, I mean at tree level everything is trivial. You're just squaring your open string integrand into closed string integrand, so you can still get tree amplitude. But everything I talk about of going to loop integrand strongly depend on this surface, and even right now we can only do planar case that you can show that you keep doing this single forward limit to give you single cut. It does give you the loop integrand that should come out from that surface integral, and at least up to the cases we checked. Okay, I'll stop here. Thank you. Very good. Yeah. So there are various contexts that classical algebra appear in amplitude. For example, also in n equals 4, super Yang Mills. There are the quivers related to the Grassmannian class algebra. Here, it's really the surface, the class algebra related to the surface. And I can show you this, for example, in the simplest case of tree level. This f polynomial I showed you are literally the f polynomial of the class algebra. Yes. So this is just type A. So if you have n external legs, then this is like n-3 dimensional type A case. So this y are exactly giving you n-3 positive variables for your space, and this fy, this roughly n squared, n choose 2 f of y are, these polynomials are particular the F polynomial of a particular choice. Yes. Yes. And if you change your triangulation, change your parameterization, it gives you some other parameterization. This is just a simple relation between tree-level string amplitude, the Kobayashi factor, and the F polynomial in type A class algebra. Yeah. Yes, so for trace by cube, there's the way to do it. So basically, you get a global Schwinger form for the whole thing. For Yang-Mills, we still don't know how to do this. I mean, formally, I think you still can do it. So, yeah, that's a very good question. Yeah, the main issue is that we don't know how to take alpha prime to zero limit of this guy at loop level. So if you can exchange the integration variable, you're actually getting something at finite alpha prime, which is even, yeah. I mean, I don't have any idea how to do that. Yeah. So if we can first turn this into a field theory statement, then it presumably, because all the loop dependence is in this exponent. So you presumably there's a way of exchanging them very similar. That's why for trace by cube it works, because it's dy over y. The alpha prime to zero limit is literally the tropical limit of this formula. Then you can exchange the two and get a Schwinger form for the whole phi cube amplitude instead of graph by graph. But for Yang-Mills, really the most difficult thing, even at tree level, is to honestly take the alpha prime to zero limit of this formula. How do you make sense of the dy over y square measure? Yeah. Yes. Yeah, I mean, this for example, for yeah, it depends on which you say. So for tree level, everything is understood, right? So for example, I showed you the shifted trace phi cube string formula literally give you the 2n scalar in Platonic string. So this is just really a rewriting of the old things we know. What's surprising is that the same shift seems to give you also loop integrand that in gluon case. But I have to say this is already very far away from the trace phi cube, because now you are dealing with some alpha prime deformation of the trace phi cube. So I cannot imagine any direct relation between trace phi cube and the gluon at loop level. So it's all based on this so-called stringy trace phi cube formula and turn the dy over y into dy over y squared. I mean, the reason, in our understanding, the reason for this is working is this constraint from gauge invariance or single cut and so on. It's not directly something we understand. But for pions, I think there must be an understanding, right? So everything we did is at field theory level. So there's nothing alpha prime. We do the shift, take the shift to infinity, which guarantee you have the correct pole structure and at zero. So I think that's how, for pions, it's a very simple model that the physical reason that it works, I guess. Yeah. Thank you.